Everything is better as a double.
Double stuffed Oreos.
Double bubble chewing gum.
Double Dutch jump rope. A double-double.
Or even double integrals. Now you may be asking yourself, what are double integrals? And I will answer that in time, but first let's start by doing a quick review of the definition of a definite integral for functions of single variables. First, when working with the integral of the function f of x, line 1, we know that x exists in the interval between some number a and some number b, line 2. Note that this does assume that a is smaller than b, line 3. We then use this expression to determine the area under the curve of f at x, which we do by breaking up the interval of a to b into n number of subinterval rectangles of width delta x, line 4. And then we choose a point, x asterisk, which is the midpoint of each rectangle, line 5. Now what we have is the complete list of all the ingredients we need for a definite integral of a single variable. Now that we have all of our ingredients, each of the rectangles, as seen here, has a height of f at x asterisk and width of delta x. So we can then calculate and use the area of each of these rectangles to approximate the area under the curve, using equation number 1. To get the exact area, we then take the limit as n approaches infinity, which leaves us with the definition of the definite integral, which, you guessed it, is equation number 2. So that's cool and all, but this video focuses on double integrals, because as we know, everything is better as a double. So now, let's take a look at how to integrate a function of two variables, f of x and y, line number 1. With functions of one variable, we integrate it over a one-dimensional space, and so it makes sense that when integrating a function of two variables, we will integrate over a region of two-dimensional space, known as R2. Line 2. We will start out by assuming that the region in R2 is a rectangle, which we will denote by line 3. This means that the range for x is between a and b, and for y is between c and d. This is line 4 and line 5. Now that we understand all this, and have the components of a double integral, let's start out with the graph of the surface S, given by graphing f at x over the rectangle R, as seen in this diagram. When constructing a double integral, it is helpful to think of the question as trying to figure out the volume under a surface. And so here, we will figure out the volume of the region under S and above the xy plane. We will first approximate the volume much as we approximated the area for single integrals. We will divide up x into n subintervals and divide up y into m subintervals. This will divide up R into a series of smaller rectangles, and from each of these, we will choose a point in the center of these rectangles indicated at x asterisk, y asterisk. Now, over each of these smaller rectangles, we will construct a box whose height reaches the surface at its midpoint. Each of the rectangles has a base area of delta A and a height of f at x asterisk and y asterisk. So the volume of each of these boxes is its base area times its height. With all this mess, I mean math, taken into account, the volume under the surface S is then approximately the expression given by equation number 1. We will have a double sum once we will add up the volumes in both the x and y directions. To get a better estimation of the volume, we will make both n and m larger and larger to get the exact volume. Therefore, we will need to take the limit as both n and m approach infinity. This is given by equation number 2, which, voila, is the equation for a double integral.